Hello guys, welcome to the video for MCC9-12.G.SRT.1 through 5. Dilation is a similarity transformation in which a figure is enlarged or reduced using a scale factor. A scale factor is a number that shows the ratio to which the old figure will be in comparison to the new figure. The center is the point on which the dilation starts. The apostrophe is the mark used to show that the point in question is a part of the new shape. Dilation is considered to be a similarity transformation. This means that the original figure and dilated figure will not have the same measure, but they will share the same shape. When a figure is dilated, it is either enlarged or shrunken by a certain amount, or a scale factor. For this pair of figures, the scale factor would be 4, which means that the dilated figure would be 4 times the size of the original figure. And in this pair of figure, the scale factor would be 1/3, which means that the dilated figure is 1/3 the size of the original figure. We can find out the scale factor by finding the ratio of the old figure to the new figure. For example, the green rectangle has a length of 6 inches and a width of 4 inches, while the blue rectangle has a length of 3 inches and a width of 2 inches. Since 6 divided by 3 and 4 divided by 2 both equals 2, this means that the scale factor is 2, because the old rectangle is enlarged to be twice its old size. Lines can be dilated too. In this case, the red segment is the original segment, and the brown segment is the new segment. Using the distance formula, you can find the length of these two segments. When you do, what do you notice? Is there a ratio between the two numbers? Pause this video, and using the distance formula, find the length of these two segments. Yes, in fact, there is a ratio of 2 to 1. Therefore, the scale factor can be determined as 2. If the dilation occurs through the center, and the dilation occurs on a segment, then the new and old segments will occur on the same line. As you can see here, this is the old segment with the points J and M, and this is the new segment with the points J apostrophe and M apostrophe. As you can see, this is where the dilation starts, which is the center, and the points J apostrophe, and M apostrophe are both on their own same lines, respectively. So, the location of the dilated figure depends on the center. In this case, the center is origin. As you can see, this is where the dilation starts, and both the original and dilated figure must line up with the center, like this. Try this. Draw the dilation of a figure with a scale factor of 2 and a center of 1 to 2. Please try this on your own. You should get something that looks a bit like this. A dilated figure that is twice the size of the original figure, and both figures are lined up with the center, which is on the point 1, 2. When dilating an object, use this rule. Take the points of the figure and multiply it by a scale factor. After you plot the new points, you will have the dilated figure. Use the formula to find the scale factor given the points. x2 over x1, y2 over y1. Using this formula will yield you the same number for both the x and y coordinates, so technically you only have to use one of these formulas. However, whichever number you get, this will be your scale factor. Use this formula to find the scale factor given the length. Length 2 divided by length 1. In this case, length refers to the distance between 2 points connected by a line segment. Vocabulary. Corresponding sides. If the relative position of two sides is the same in two figures, then they are corresponding sides. Corresponding angles. Two angles that are in the same relative position in two figures. Similarity. Two figures whose corresponding angles have the same measure in proportional corresponding sides. Similarity transformation. A dilation or a composite of one or more dilations and one or more congruence theorems that maps one figure to the other figure. We said that dilated figures will always be similar. However, we can prove that two figures are similar using corresponding angles and sides. Using what we know of similarity, can we say that the original and dilated figures are similar? Well, looking at them straight away, we can say yeah, because they're the same shape but they're not the same size. However, let's look at this mathematically. The corresponding sides are proportional. 12 divided by 6 and 8 divided by 4 both equals 2. And the corresponding angles are both equal, with 90 degrees. So, are these two figures similar? Yes. Yes, they are. Try this. Which pair of figures is similar to each other? Please take the time to now circle your answer. The correct answer is the first pair, because the two figures have the same shape, yet different size. The second pair of figures are not similar, because they have different shape and have the same size. And the third pair of figures have the different shape and different size. Figures can be modified by multiple transformations, including translation, reflections, and rotations. For example, dilation with reflection. That's a combination of a similarity and congruence. In this case, this figure has been dilated, rotated, and reflected across the x-axis in order to get it to this point. Vocabulary. AAA theorem. Otherwise known as the angle-angle-angle theorem, the AAA theorem is used to prove that two triangles have equal corresponding angles if and only if their corresponding sides are proportional. SSS similarity theorem. The SSS theorem, or the side-side-side theorem, states that if three sides of one triangle are proportional to three sides of another triangle, then these two triangles are similar. SAS, or similarity theorem. The SSS theorem, or the side-angle-side theorem, states that if two sides and the included angle of one triangle are proportional and equal to two sides and the included angle of another triangle, then these two triangles are similar. Included angle. When two lines meet at a common point, the angle between them is called the included angle. We can determine the similarity of two figures by using AAA, SSS, and SAS theorems. Every triangle, regardless of its side lengths, will always have an internal angle measure of 180 degrees. Depending on the type of the triangle and the length of the sides, we can use the similarity theorem to determine whether or not the two figures are similar. The AAA theorem. So triangle 1 consists of angle 1, which is 45 degrees. Angle 2 consists of has 30 degrees, and angle 3 is 105 degrees. Triangle 2 consists of angle A, which is 45 degrees, angle B, which is 30 degrees, and angle C, which is 105 degrees. Triangle 1 has side lengths of 2, 4, and 3, and triangle 2 has side lengths of 4, 8, and 6. Now, forget that we have the angle measures. Look at only the sides. Are these sides proportional? Yes, they are. 2 divided by 4, 4 divided by 8, 3 divided by 6, or vice versa. That will get you the same number all around, which means that these are proportional. The corresponding sides are proportional. So already we must know that these corresponding angles must be equal to each other. And are they? Yes, in fact they are. Using the description, yes they are. And this is because no matter the sides, each angle will always have an internal angle measure of 180 degrees. It just depends on the triangle's side lengths in order to figure out what these angles will be. In this case, even though they're proportional, different sizes, they will still have the same angle measure because they are proportional. SSS similarity theorem. So triangle 1 consists of angle 1, angle 2, and angle 3. Triangle 2 consists of angle A, angle B, and angle C. Triangle 1 has side lengths of 3, 3, 3, and triangle 2 has side lengths of 6, 6, 6. Now, 6 divided by 3, 6 divided by 3, and 6 divided by 3. Well, that'll get you 2 all around. So can we tell that these two figures, using the SSS theorem, are they similar to each other? Yes, in fact they are. Because they are the same shape, yet they have different sizes. SAS similarity theorem. Triangle 1 consists of angle 1, angle 2, and angle 3. Triangle 2 consists of angle A, angle B, and angle C. Triangle 1 has side lengths of 4, 6, and 8, and triangle 2 has side lengths of 2, 3, and 4. Now, let's say that the sides on triangle 1 is sides 1 to 3, which would have the side length of 4, and 3 to 2, which would have the side length of 8. And on triangle 2, the sides would be A to C, which should have the side length of 2, and C to B, which should have the side length of 4. Now, in this case, in triangle 1, the included angle would be 3, and in triangle 2, the included angle would be C. Now, are the sides proportional to each other? 2 divided by 4 is 0.5, 4 divided by 8 is 0.5 as well. So yes, they are proportional to each other. And are the corresponding angles proportional to each other? Yes, in fact they are. Because we can actually use the SSS theorem to prove that. Or, the AAA theorem, my apologies, because each of these corresponding sides are proportional to each other, and thus, using the AAA theorem, that must mean that each corresponding angle must be equal to each other. So, since we know that these are now equal to each other, can we say that using the SSS theorem, that these two figures are similar? Yes. Yes, they are. Use the SSS similarity theorem to prove that these two figures are similar to each other. So, SSS theorem. Is each corresponding side proportional to each other? Yes, in fact they are. Because 2 divided by 5 is 0.5, 1.5 divided by 3 is 0.5, and 3 divided by 6 is 0.5. So yes, these two figures are similar because they are the same shape, yet they do not have the same size. Vocabulary. Pythagorean theorem. The Pythagorean theorem says that the square of the hypotenuse is equal to the sum of the squares of the two other sides. Side splitter theorem. When a line that cuts into a triangle is parallel to one side of the triangle, both sides of the split triangle are proportional to one another. The Pythagorean theorem can be used to determine the length of both the hypotenuse and the length of the triangle. Use this formula a squared plus b squared plus c squared equals c squared to find the lengths of the side. In this formula, a and b are the variables to replace by the length of the triangle legs, in this case right here, and c is the variable to replace by the length of the hypotenuse, right here. Using the Pythagorean theorem, we can find the length of c. So, a squared plus b squared, which is 6 times 6, which equals 36, and 12 times 12, which is 144, equals c squared. Add these two together, you get 180, then you find the square root of both of these numbers in order to get c by itself, and you get the value of c. You do the same thing here, and instead of finding c, you're finding b. So you need to subtract a from this side, and then find the square root of b from 64 and b squared in order to get a. Find the value of a. Please find the value of a and pause the video. This is what you should have done in order to get the value of a. You can determine the length of the side using the side splitter theorem. As you can tell, these sides are all proportional. If you go out and divide each of these numbers, you'll find that they equal the exact same measure. Try for yourself. Using these points, are they proportional to each other? Yes. 6 divided by 3, 2. 16 divided by 8, 2. 10 divided by 5, 2. They're proportional. Vocabulary. Congruency. When two figures have the same size and shape. ASA theorem. If two angles in the included side of one triangle are congruent to two angles in an included side of another triangle, then the two triangles are congruent. AAS theorem. If the angles in the non-included side of one triangle are congruent to two angles in a non-included side of another triangle, then the triangles are congruent. HL theorem. If the hypotenuse and leg of one right triangle are congruent to the hypotenuse and leg of another right triangle, then the right triangles are congruent. SSS congruence theorem. If the three sides of one triangle are congruent to the three sides of another triangle, then the triangles are congruent. SAS congruence theorem. If the two side angles and the included angle of one triangle are congruent to two sides and the included angle of another, then the triangles are congruent. And the CPCF theorem, which is congruent parts of congruent figures are congruent theorem. If the two figures are congruent, then their corresponding parts are congruent. And a non-included angle is an angle that is not on the intersection of two specified sides. So the ASA theorem. So, angle, side, angle. Are these two shapes congruent? Yes, they are, because they have the same length, corresponding angle measurements. Angle, angle, side. Angle, angle, side. And then the non-included side, right over here. This is not included in this side. And so yes, they would be, according to ASA, congruent. Hypotenuse, leg. Since the hypotenuse and the leg, which is right here, the right angle, since they're congruent, yes, they would be congruent to each other. SSS. This is simple. They're the same lengths, same size, therefore they must be congruent. Side, angle, side. Since this and this are congruent, and this is congruent, this means that this must be side, angle, side. Side, angle, side. CPFC. So going back to SAS, pop this in there. Can we say that these are congruent? Yes, because since we know that these two triangles are congruent, we can say that their parts are congruent. Now, we can use these theorems to prove relationships. For example, in graphs, like this. Please take the time to copy this graph down. That is the end of the video. Thank you for listening. I hope you learned well. Thank you again. Good luck.